All right, guys, let's start. Okay. So now we are doing your chapter number three, or sorry, lesson number three of chapter one, right? Which is basics of derivatives and integrals. Okay. This is not your financial derivatives, guys, right? So, see, when we talk about your derivatives, right, we are looking at it from the perspective of mathematics, right? So, we understand that calculus is the mathematical engine behind your modern finance. Every major financial model uses your calculus, whether it is option pricing, whether it is portfolio optimization, whether it is interest rate model, whether it is risk management. So all these, right? All these things, all financial model uses calculus. Now, inside calculus, there are two tools, right? One tool is your derivatives, and one tool is your integrals. Derivative as a tool, right? When you think about derivatives as a tool, right? Derivative as a tool, that is this one. Measures changes, right? And integrals measures your accumulation, right? So there are two tools inside calculus. One is measuring your changes. Other is measures your accumulation. Okay. So we start with your derivative first and we'll try to understand, right? One is for the changes, one is for the accumulation. Okay. All right. Now, what is the derivative? Again, please try to understand. Start with a very intuitive understanding here. A derivative measures how fast something changes. Okay. Now, in finance, we constantly ask how fast is the price changing? How sensitive is an option to the underlying asset? How quickly is the risk increasing? So once we know that, I think the ideal tool for that is your derivative, because derivative of a function measures the instantaneous rate of change of one variable in respect or with respect to another. It answers the question how fast is the financial quantity changing at a given point of time. Common definition, f dash x is equal to limit h tends to 0, fx plus h minus fx divided by h. Okay. This is the change in the function, right? Then the numerator is the change in the function. Denominator, right, is a change in the input. Then we are taking the ratio. This is the rate of the change, right? Rate of the change. Okay. Now, when we take the ratio, right, where we are looking at your rate of change, right? So what we are doing is when we're putting limit to it, right? Limit h tends to 0, right? We are trying to figure out, we are trying to meaning the change becomes infinitely small. So we get the instantaneous rate of change. The geometric interpretation of this is very important. Please understand derivative is like the slope of the tangent line. If the slope is steep, your function changes rapidly. If the slope is small, function kind of changes slowly. Okay. So have the geometric interpretation as well, right? Again, I'm repeating very, very clearly that we are trying to figure out a ratio. This is the rate of the change. When you take the limit, which means that we are trying to find the change, the change becomes infinitely small, so we get the instantaneous rate of change. And when you try to do the geometric interpretation, please understand derivative is like the slope of the tangent line. If the slope is steep, function changes rapidly. If the slope is small, function changes slowly. When you look at the financial interpretation, please understand derivatives measure your sensitivity. Example is price sensitivity, then risk sensitivity, then option sensitivity, which is Greek, right? Which we need to understand. Okay. So rate of change of price with time, this shows how fast the price moves. Then option price sensitivity, which means delta, right? A Greek, and speed at which returns or risk exposure changes, that also we understand. Okay. Another thing is that a quick check here is that if derivative is large in magnitude, a small input change will lead to a large output change. Means the system is very sensitive. This is exactly what the traders call your high risk exposure, right? If fx is large, f dash x is large in magnitude, what does it say about risk and sensitivity? Means small input change leads to large output change. System is very sensitive, highly sensitive. Okay. And this is exactly what your traders call your high risk exposure. Okay. All right. Then we go to your common derivative results. Okay. Common derivative results. Again, there are standard derivatives. If you look at your kind of function and derivatives, you have constant C, derivative is 0. You have a constant which never changes. Your linear function, they do d by dx of your x. It becomes 1. So this is 1. Okay. So slope of line when y is equal to x is always 1. Okay. Slope of line when y is equal to x is always 1. Okay. Then we have, this is called your power rule, d by dx x raised to power n will become nx n minus 1 power rule, right? This rule appears everywhere in finance. Then we have exponential function, your d by dx of ex is equal to ex, right? Exponential functions dominate finance in your continuous compounding, in your Black-Scholes model, in your geometric models. Then you have logarithmic. D by dx of ln x, which is 1 by x, used heavily in your log returns. Why these rules kind of matter is because these derivatives are used constantly in your derivative pricing, your portfolio optimization, your volatility modeling, your risk sensitivity calculations. So very, very important. Okay. Then we have your chain rule, which is very important in finance. When one variable depends on another variable, example, let's say option price depends on your stock price depends on your time. So mathematically, function is y is equal to fu, right? Function of u, and u is equal to gx. So dy by dx is equal to dy by du and du by dx, right? So that is what we need to understand. If you look at the financial example here is, please note that when v is equal to fs and s is equal to st, right? It will be done ahead. Okay, it is not done ahead, but we can do it here. V is equal to fs, s is equal to st. And if I do your, let's say, dv by dt, I can do your dv by ds into ds by dt, right? So overall interpretation here is that option price changes because stock price changes. Stock price itself changes with time. Option price changes because stock price itself changes with time, because ds, right, is indeed dependent on dt, right? So this idea kind of appears directly in your Black-Scholes PDE, the differential equation, and this is what we need to know. Then we go into delta, right? Which this is basically the financial application of derivatives. Now we are trying to collect your calculus to the real trading. Traders call derivative of your option price, and these are called your Greeks. Okay. One of the most simplest of Greek is delta, right? Greeks measure your risk sensitivity. Delta is basically measuring the sensitivity of the option price with respect to change in the price of the underlying asset. So delta is equal to delta V by delta S, meaning changing your option price when underlying price kind of changes. So that is what we need to understand. Let's say delta is equal to your 0.6. Okay. So delta is 0.6. Stock goes up, right, by rupees 1, right? So option price approximately changes by or increases by by 0.60. Okay. The financial interpretation of this is that delta measures your directional risk. Okay. High delta, what does it mean? High delta basically means option price moves strongly with your stock, right? Why traders kind of use it? Because delta is used for delta hedging, right? If you hold, let's say, call option with delta 0.6, right? You short 0.6 shares per option to hedge, right? Please understand, uh, if you're not studied hedging, it might be a little confusing. But basically, you use options to hedge your stock exposure, right? So if you have, let's say, uh, call option, right? Call option with delta. Now you have to hedge it with stock, right? So if you have positive delta there, you have to short because ultimately the objective is what? You have to get delta neutral, right? Delta neutral, if you have to get, means delta neutral means zero, neutral means zero. You have to get plus and minus. If something has plus exposure, you will hedge it by negative exposure, right? So you have call option with positive delta, you will hedge it by shorting the uh, option, shorting the stock, right? Okay, call option usually positive delta, put option usually negative delta, right? Financial application, delta hedging, portfolio manager adjust position in the underlying asset to neutralize your prices. Okay, all right. Now, when we consider this one, right, delta measures the sensitivity to the underlying price. Okay, delta measures the rate of change of the option value with respect to the underlying price, which we discussed, right? Delta V is your change in the value of your option value. V is the option value. Underlying asset price is your delta S. It represents the first order sensitivity of the option price. And graphically, it is represented like this, right? So this is, again, this is just for your knowledge. This is call option delta, right? The value lies between 0 and 1. When you take put option delta, right? Put option is other kind of option. When you take put option, right? Value will lie between your -1 to 0. It is only that there is a difference in the sign, right? Ultimately, it's 0 to 1 only, but the put option is opposite, right? Put option actually the rate of change happens in the opposite way, right? Because as the stock price increases, the put option value decreases, right? Here, when the stock price goes up, right? Underlying price goes up, the call option value goes up. Here, the stock price goes up, the put option value actually comes down, right? So that is the reason, right? You should understand. And that's why it's given -1 to 0. Otherwise, not much big of a difference, right? And see the graph. And if you think about it, this is your at the money, right? This is in the money when it is 1. This is out of money, right? So there is a concept called moneyness in the options. If you don't know, don't worry about it, right? Moneyness in the options. So the delta of an option also depends on the moneyness of the option. See, I tell you all this advanced concept because I want to correlate advanced concepts with your basic mathematical concepts. But sometimes what will happen is that a student who is new to the world of finance, right? For him, it might be very new, right? So he might get confused that, okay, I don't know what is at the money, in the money, OTM, right? So don't worry, right? When we'll study the financial portion of it, then these things will make more sense. But my duty as a teacher is that I cover these things as well, right? So that there is a uh, comprehensive coverage, right? Comprehensive coverage we have. Okay. All right. Okay. Then we go to the gamma, right? Gamma measures the rate of change of delta. The rate of change of delta with respect to the underlying price, which is this, right? Gamma measures how fast the delta change, how fast delta itself changes. Right? How fast delta itself changes. Okay. So that's what we are trying to cover. Right. So it captures the curvature of the option value with respect to the underlying price. So we understand very clearly that it's a second order sensitivity. Second order sensitivity basically captures the convexity, the curvature, which we have studied in the functions also. Now, when you have high gamma, right, interpretation when we take high gamma means that small price movements will lead to large changes in delta, right? So this creates a non-linear risk, right? So curvature, non-linear risk, right? High gamma means the delta changes quickly as asset price moves. Important for options that are close to the strike price, which is ATM options. At the money, the gamma is highest for ATM option. When you say near at the money options, gamma becomes very, very large. This is why traders watch ATM options carefully, especially near the expiry. When you look at your trading insight here, right? So professional option traders monitor your delta for the directional exposure and gamma for the curvature risk, right? So delta was for what? Delta was for your directional exposure. Okay, gamma. Gamma is for curvature risk. Okay. Together they determine your hedging strategy. Overall, it's a very simple kind of strategy for or very simple analysis, right? Students must understand that derivatives measure how your things change in finance. Whenever we try to understand how price changes, how risk changes, how option sensitivity behaves, we use derivatives such as delta gamma. Delta is equal to your change in the option value for changing the strike price, which is the option sensitivity to price. Your gamma is equal to your rate of change of delta. Derivatives are the largest, or derivatives are the language of risk. Greeks are simply derivatives applied to finance, right? And it helps trader understand how frequently a delta hedge portfolio must be rebalanced. So why a delta hedge portfolio? Basically, what you need to understand is that when we do the hedging, right, the hedging also is done in multiple steps. If we have to do a simple kind of hedging, there is delta neutral hedging. Delta neutral hedging means you make the delta zero. You focus only on one Greek and you make delta neutral, means delta is zero. But sometimes what we do is we go to advanced form of hedging. So there we focus on two things. We want delta is equal to zero. We want gamma is equal to also zero. But again, see, hedging when you go to the advanced level of concept in hedging and risk management, then you will realize very clearly that hedging has a cost, right? You can do best of the hedging, right? But don't forget that whatever you do in hedging, right, that involves a cost, right? So hedging cuts the upside, cuts the downside, but there is a cost, right? There's a cost involved. And then you have to make a judgment, right? Whether would you want to pay that cost or not, right? Not every risk is supposed to be hedged. Please, it's not a black and white thing that you see a risk, you hedge it. No. You only hedge a risk which you believe should be hedged, right? And this decision comes from the board of directors and the risk management committee and that's a separate risk management department, right? So not every risk has to be hedged, but you have to hedge risk which kind of have the capacity to uh, interrupt your business, right? So that's a judgment call which you have to take, right? But what I'm trying to say is that if you do a first level kind of hedging, that you delta neutral hedging, where you do delta zero, which I showed you previously also, that if the call option is positive delta, will short the stock, so plus minus becomes zero, right? And then I'm saying the delta neutral you have done, then you go into gamma neutral hedging also, because you want to put gamma is equal to zero also, because that time basically delta neutral hedging, you are only hedging for the directional exposure, right? You're hedging only for the linear risk. When you go for delta and gamma, you are hedging not only for the directional exposure, you're also hedging for the curvature risk, non-linear risk also, right? And which happens specifically in a very short time frame near the expiry. So you want to capture that also. But again, see, when you're doing two types of hedging, it's double the cost or maybe more than that, right? So you should be ready to pay it if you want that kind of security, right? Indicate the level of non-linear price risk. Okay. All right. Fine. Now we are getting into, after we have seen delta, right? Delta, which was sensitivity to your underlying price, where we started the very simple idea of when the stock price moves, the option price also moves. The question is how much does the option price moves when the stock moves, right? That was sensitivity of delta, right? So delta V by delta S, delta was measuring the rate of change of option price with respect to stock price, right? That was it, right? And we saw the graph also, right? Uh, and I told you about delta hedging as well. Gamma also I told you, gamma measures how your delta changes, second derivative, curvature, right? High gamma means delta changes very quickly. Gamma becomes very high near the ATM option I told you, right? So that is what I explained. Okay. Now, here we are getting into again the same thing only, right? We are trying to convey to you that gamma measures the non-linear risk, right? Delta assumes linear movement, gamma measures the non-linear risk, gamma calculates the curvature risk. Okay, and there is a horizontal axis, which is the stock price. There's a vertical axis, which is the gamma, right? And what we are trying to understand here is that gamma, if you take out of money, right? If you take out of money, OTM, deep out of money, deep OTM, gamma, right? Gamma is almost like equal to zero, right? Approximately equal to zero. So delta hardly changes. Delta hardly changes. Gamma is almost equal to zero. And when you have near strike price, right? Gamma peaks, right? This is ATM. So small stock movements causes large delta changes. Okay, small stock movements cause large delta changes, right? And we go deep in the money, delta stabilizes what you kind of when you go deep in the money, right? Gamma declines again, right? And delta stabilizes near one, right? So again, this is your uh, thing, right? So it's a peakedness which happens at the money. At the money options are most sensitive. At the money options are kind of when you say hardest to hedge, most actively traded. See, it is zero value, right? So it is OTM also zero value, ITM also zero value, right? Highest for the ATM, and that's why hardest to hedge, right? It captures the curvature of the option price and indicates how rapidly the hedge ratio to the changes at the underlying price moves. Fine. Then we go to theta, right? When we talk about theta, what is to understand here is theta measures the sensitivity of the option value with respect to time. Theta is equal to delta V by delta T, changing the option value with respect to time. We are basically talking about time risk now. Okay, delta and gamma were measuring your price sensitivity. Theta measures your time sensitivity. Basically, it reflects how the value of an option decreases as time passes, commonly known as your theta decay or time decay. Option lose value as time passes. This is called your time decay, right? Call option price today, if it's 10, 1 week later, everything unchanged, right? Call option value might be 9.70, right? This is the loss 0.30 comes from theta. Please understand the loss will only be to the buyer of the option. If the seller of the option, it will be a gain, right? So most option lose value as you close to your expiry. So theta for long position is always negative. Uh, Theta for short position is positive. As you approach the expiry, uncertainty reduces, time value decreases, so option value kind of declines. Then look at your trading application, let's say in the trading world, right? Theta is extremely important for your option sellers. Option sellers benefit from your time decay. You have strategies such as a covered call, your short straddles, your iron condors, right? When you're option buyers fight against time decay. That's why they look at the momentum. They need strong price movement. And if you look at your uh, calendar spread, option selling calendar spread, they're all, these strategies are used. Traders monitor theta to estimate the daily loss and option value. And there is detailed understanding here also. Theta is, let's say, equal to minus 0.25. Option loses about 0.25 rupees per day due to your time decay, right? Overall, please understand delta is for price risk, delta V by delta S, gamma is for non-linear price risk, theta is for time decay. A professional options trader manages many kinds of risk, right? So he has to manage your price risk. If price risk has to be managed, he has to think in delta. If he has to manage your curvature risk, he has to manage your gamma, right? If he has to manage your time risk, he has to manage your theta, right? If he has to manage your volatility risk, he has to manage your vega. Okay, so that is what we need to understand, and there are various graphs also I had given to you, so we'll try to study those. Okay. Now look at your theta time decay of option value, very, very important graph, right? We are trying to show or measure the sensitivity of the option price with respect to the passage of time. It captures the phenomenon of time decay, where the value of an option generally decreases as the expiry date approaches, which is delta V by delta T. You start with a very fundamental observation that option lose value as time passes. Why? Because the probability of a large price movement shrinks. Probability of a large price movement shrinks as the expiry approaches, right? Expiration approaches. This decay is measured by a theta. And you see here, right? What we are trying to show you here is that how there's a decay which is coming, right? How the value is, as you're going closer to expiry, how the value is kind of collapsing, right? So theta is measuring how option value changes as time passes, right? So every day that is passed, right, reduces the remaining opportunity for the option to become profitable. So an option buyer has to be careful, right? Especially the weekend is coming or long holiday is coming. There is a, this consideration has to be kept in mind, right? For most long option, theta is always negative. For most short option, theta is positive, right? Horizontal axis here is time to expiry. Vertical axis here is theta. The curve becomes more negative near expiry, meaning time decay accelerate. Time decay accelerate. Expiry approaches, right? So early in the option life, time decay is slow. Near expiry, time decay very fast. Option sellers benefit from your theta strategies, which are defined, or strategies which are made to capture a time decay, such as your short straddles, short strangles, covered call, iron condors. So option buyers must overcome your theta with strong price movement, right? That is what we look at. Okay. Then we have Vega, right? Vega is your sensitivity to volatility. Vega is sensitivity to volatility, right? So we are introducing now the volatility risk. Okay. Vega is the sensitivity to volatility. Okay. So again, what we are looking at, where, see, these are those Greeks which are not so important, but see, if you are becoming a professional trader, if you are working at a desk in Goldman Sachs, HSBC, other places, you have to learn this, right? So we are introducing the volatility risk. Option price depend heavily on volatility. Higher volatility means higher probability of large price moves. That increases your option value, right? So Vega measures how your option price changes when the volatility changes, right? So here the formula is change in the option value for the change in volatility. Sigma here is the volatility, right? So that is what we have. If volatility increases, the option value increases. We know that, right? Because more volatility increases, the probability of finishing in the money increases. Let's say call option price is, let's say 10 rupees, volatility increases, call option becomes 11. The $1 change is captured by Vega, right? So the graph, which you can see here, shows how Vega versus stock price moves. Again, at the money option, right? At the money option are most sensitive to volatility, which is you have to understand if you compare in the money, right? Out of money and in the money, right? They are deep in the money, deep out of money, right? Both are not what you say uh, more that sensitive, right? So ATM options has maximum Vega volatility traders, right? Who focus on volatility, right? And especially in this geopolitical context, right? When there is so much of volatility, whether you see oil prices and other things, right? Volatility traders focus heavily on Vega strategies that are defined to trade volatility, your straddle, your stranger, volatility arbitrage, right? They use this concept, right? So keep that in mind. Okay. Then we get into your row. When you take row, right, we are introducing your interest rate risk. Let's say interest rate risk, options are also affected by your interest rate, right? Row measures the interest rate sensitivity. You measure the sensitivity of row, which is given as a change in the value of option to change in the value of your rates, interest rates. R is the interest rate. If interest rate increases, call option value usually increases, right? Right. This sounds little difficult to understand, right? Normally, people don't think like this. People think that when interest rate increases, equity value will go down and the call option value will go down, right? But this is not so, right? It is very uh, tricky to understand. Basically, idea here is that see people invest money in markets to earn more than the, and I'm telling you the definition which is given in your famous book, John C. Hull's Option and Derivatives. So the idea here is that people think that when interest rate uh, rises, right, the equity will fall down and the call option value will go down, right? But it doesn't happen like this. Basically, people, let's say, invest in equity markets. They think that I'm going to, let's say, somebody earns in fixed income, somebody is earning 4%, US market, right? So now, and he's earning in equity market 10%, right? So he's earning an incremental alpha of 6%, right? So he's happy. Now, let's say the interest rate in US market rise to 4 to 5%, right? In that case, the person who is investing in equity market thinks that he's taking more risk and he's only earning 5%. So then the behavioral economics kicks in and he thinks that no, if you are investing in market, you need to still earn 6 or more than 6. Then the expected return in the market also goes to 11%, and that forces the stock price to go up. And similarly, the stock price goes up, the equity goes up, the call option also goes up, right? So very tricky to understand, right? Very tricky because in a simple, usual way, you will not understand it. But the idea here is, see, you can remember the final result, that's one thing. But the other idea is that you understand that when interest rate goes up, the call option price goes up. Why? Because the present value of the strike price kind of decreases. You effectively pay the strike later, right? So now here the graph shows a positive slope, right? It's a positive slope we can see. And as interest rate increases, the option value increases, right? So row matters most for your long dated option, right? Long dated option. Right? For your interest rate derivatives, right? For your FX option, right? For short dated equity option, rho is usually small, right? So that is what we need to understand. Please keep that in mind, right? So it matters more for long dated option, interest rate derivatives, FX option. Short dated option, slow, rho is low. Okay, remember that. Now we are getting into another example, portfolio growth example. Consider the value of a continuously growing investment VT is equal to V naught ERT, right? V naught is the initial portfolio value, R is the continuous growth rate, T is the time. Derivative with respect to time, you take the dV by dt, right? So this is how RVT you get, right? V naught is the initial investment, R is the continuous growth rate, and T is the time, right? So we took the derivative, ERT becomes RERT, right? Derivative of ERT, right? Just for your knowledge. We take derivative of ERT, right? ERT becomes R comes ahead, RERT, and V naught remains same, right? So if we have dV by dt, it becomes RVT, right? So RVT we get, right? So what we are trying to understand here is, or what we get here, right, after taking the derivative, is the basic idea: the growth rate of the portfolio is proportional to its current value, right? Meaning the bigger the portfolio becomes, the faster it grows, right? Bigger the portfolio, the faster it grows. Okay, this is your exponential growth, which you need to focus, and very important, this equation, right, which we are getting here, dv by dt to rvt, right? This is basically bigger the portfolio, the faster it grows, right? So this equation describes your compound interest, your portfolio growth, your economic growth model. Intuitively, portfolio value kind of doubles, growth per unit also doubles, right? So very, very important, right? Very, very important, right? This is derivative. This derivative shows how fast the portfolio value changes, changing at time t, right? So overall, the focus here is that we are looking at delta, we are looking at gamma, we are looking at theta, we are looking at vega, we are looking at rho. Delta is price sensitivity, gamma is curvature risk, right? Non-linear price risk, theta is your time decay, vega is your volatility risk, rho is the interest rate risk. And professional option traders, people who work in quant finance, are not trying to predict your price. They are managing 5 dimensions of risk. One is your linear price risk, one is your curvature price risk, one is your time, one is your volatility, one is your interest rate, right? And that's what you need to understand very, very clearly. Okay. Now, once we have seen this, we are getting into the next part. We have covered the derivative part, we have covered the Greeks part. Now we are getting into integral. So after doing derivative, we are moving to your integral, which is the mirror image of derivatives. Derivatives tells us how fast something changes. Integral tells us how much change accumulates over time. So what is an integral? You start with the, again, let me write it down. If derivative integral tells us how much change accumulates over time. Okay. Now, what is an integral? Let's start with a very simple understanding. See, an integral basically measures your accumulation, right? Integral measures the accumulated value of quantity over time or space, right? So whenever we have to find out your accumulated returns, whenever you have to find the accumulated cash flow, whenever we have to find the total probability, whenever we have to find the total profit loss over time, then we take the accumulated value, right? Mathematical definition is given here. It is the integral from a to b fx dx, right? This represents the total accumulation of function fx between your a and b, right? It is the area under the curve between a and b, right? Then we move into your indefinite integral, right? Indefinite integral. This is kind of fx dx gives you fx plus c. Basically, this represents the antiderivative of fx, right? Meaning if your f dash x is equal to fx, integral of your fx dx gives you fx, right? So key idea here is derivative is rate of change, integral is the total accumulation of that change. Okay. Now, in finance, right? If let's say there is instantaneous return, right? RT. Then if you take the integral of instantaneous return RT dt, it gives you total return over time, right? So if you have, let's say, RT, and you take the RT dt, it gets the total return over time. Okay. So look at the financial interpretation of integrals. Integrals appear everywhere in your finance. They convert your rates or flows into your total values, right? There is total return over time, right? Which I told you very clearly. You can, if you want to find total return of time over area A to B, right? That also we can do. Intuition here is that each instant contributes a tiny return. The integral add all those tiny returns kind of together. If return is kind of your constant, RT is equal to 0.05, then you can take for time period, let's say 0 to 1, 0.05 dt is 0.05, meaning 5% of annual return, right? It gives you the total effect, right? It gives you the total effect of that change, right? Which is here, right? Which is given here. Total return of time, right? So it is taken, let's say, right? So if you take RT is equal to your 0.05 dt, and I take 0 to 1, and that's give me 0.05, right? Meaning there's a 5% annual return, right? Then accumulated cash flow when we take, so suppose cash flow occurs continuously, right? Present value becomes your integral from 0 to t, CFT exponential minus RT dt, meaning CFT is basically your cash flow at time t, minus RT is discount factor. The integral sums all your discount cash flow over time. Where it is used in the application part, infrastructure valuation, dividend discount models, the bond pricing model, etc. Right? Then we have your probability and risk. There we use integral also appear in your probability for a probability density function fx, right? If you take probability of a to x to b, right? So AV fx dx, right? This represents the area under a probability density function PDF, right? So probability is simply area under the distribution. For example, in a normal distribution, probability of return lying between two values is computing using an integral. Integrals basically convert rates to total, flows to your accumulated values, right? And your densities into your probabilities, right? So that is what we are getting here. Converts your rates to totals, densities into probabilities, your flows into your accumulated values. This is your flows. You are converting into accumulated values, rates, right? Rates into total return. Your densities into probabilities. Okay, so that is what we need to look at. The then we go into your present value of continuous cash flow. Now we're trying to connect your integral to your valuation. Suppose a project generates your continuous cash flows, let's say CFT. All right, CFT be the cash flow rate at time t, the present value we are taking, right? CFT, exponential minus RTDT. The component CFT is the cash flow rate, R is the discount rate, T is the time horizon, Y exponential discounting, E minus RTDT represents your continuous discounting. Right? You look at the interpretation part, each future cash flow is discounted back to today. Right? The integral sums all discounted values, all discounted flows over time. Right? That is what we are doing. If you look at CFT, is the cash flow at time t, R is the continuous discount rate, T is the time horizon. Interpretation is exponential minus RT discount future cash flows today. Right? The integral sums discounted cash flow over time. Right, and then we look at your applications, valuing infrastructure project, continuous dividend models, interest rate, and bond pricing models. Right, real finance application when you look at using all these things, even in your energy project valuation, your dividend discount models, your bond pricing, your interest rate models, we all use this thing, right? Very common. Okay. Then we go to your expected value from a probability density function. Now we are basically connecting, right? We connect integrals with your statistics and risk. We connect integral with statistics and risks. Now we're connecting integral with statistics and risks for a continuous random variable x. If you see expected value x, which is between infinity and minus infinity, x fx dx, right? Fx is basically your probability density, right? Fx is the your given the likelihood outcome. We can call it probability density also, right? Each outcome x is weighted by its probability. So integral calculates the probability weighted average. What is the understanding here? Basically, expected value is what? Simply the average outcome weighted by the probability, right? So if you are getting confused, this is nothing, guys. This is expected value, right? The expected value x fx dx. So expected value, this is a general formula, right? When we take the general formula, this is the value of the expected value, right? So this is a definition, right? So see, expected value is not exactly a concept of mean, right? Expected value is if you carry on an experiment for infinite number of time, what is the expected value we get in a certain kind of experiment, right? Just for example, let's say you roll a dice, right? If you roll a dice, then you have to, if you same case, right? You roll a dice, your possibilities are your 1 to 6. Right, and if you take x fx dx, that case, it becomes 1 into 1 by 6 plus 2 into your 1 by 6. X is 1, 2, right? 3 into 1 by 6, 4 into 1 by 6, 5 into 1 by 6 plus 6 into 1 by 6. Now you 1 by 6 common, and you have 1 plus 2 plus 3 plus 4 plus 5 plus 6, right? So which makes 1 by 6. 6 plus 5, 11, 15, 18, 20, 21. 21 by 6, which is 3.5. Now, what is interesting to understand here is because when you throw a dice ever, right, you either get 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. But the expected value is 3.5. Will you ever get a 3.5 value when you throw a dice? No, you will never get a 3.5 value when you throw a dice. Right? So this is the interesting part. The expected values is a concept which is very close to mean, right? But you should not think that it is one of the expected values. No, right? It is one of the values which come in the process, right? It can be different values also, right? So remember that again, this is a definition, right? X fx dx is a definition. You have taken the integral, right? You can do it for anything, right? You can take. You have taken a dice thing. You can take, suppose the possible returns are 2%, 5%, 10%, right? Each with some probability, right? The expected return is the probability weighted average. The integral basically performs the calculation for your continuous distribution, right? Now, when you look at your financial application, Whenever we have to use your asset return models, whenever we have to use your portfolio theory, whenever we have to use your risk measure, whenever we have to use your option pricing, right? We use these kind of things, right? For example, let's say we are using your Black-Scholes, right? So option price is essentially your expected value of payoff, right? In Black-Scholes, option price is your expected value of payoff, right? So it is computed under your risk neutral probability, and this expectation is calculated using an integral, right? Integral, right? In the derivation, it comes a integral, right? So in the Black-Scholes, I'm not going into there in deep, but I'm just trying to tell you, in Black-Scholes model, option price is the expected value of the payoff. In binomial or pricing model, you take the expected value mechanically or manually, just kind of take the probabilities, multiply by the probability, and then you find out, right? But in your, there are two models, right? Binomial option pricing model, Black-Scholes option pricing model. Binomial option pricing model, you follow the process of what you do. You take the probability weighted average payoff, right? You take the probability average weighted average payoff, and then you find the option payoff, right? So expected value is the, or option price is the, you find the payoff, which is probability weighted, and then you take the expected value of the payoff. In your Black-Scholes model, you again find the payoff, but not probability weighted there. You use the integral, right? And then you try to find the option price, right? We'll see when you go to Black-Scholes, right? So overall, what we need to understand is that expected value is a probability weighted average computed by your integration. Derivatives and integrals form the mathematical foundation of finance. Derivatives focus on the rate of change. Integral focus on the total accumulation. Derivative use cases are generally your Greeks, your sensitivities. Integral use cases are your present value, your returns, your probabilities. In your modern quantitative finance, is built on your two ideas, measure how fast the things change. Your derivatives measure how those changes accumulate. Your integrals together, they power models like your Black-Scholes, your interest rate models, your portfolio optimization, your risk management, etc. Right? That is what we need to do. Okay, keep that in mind very clearly. Okay, very, very important. We'll do the Black-Scholes, interest rate model, portfolio optimization, risk management when we reach there. Right now, again, understand the objective. We are trying to, my objective is to give you that, okay, these concepts will be used in those models. My idea is not to teach those models right now, right? Because those models itself will be a 1 hour lecture, right? That we don't want to do right now. But at least give you an idea, mapping. Okay, this concept, your derivatives, integrals, how they're related to the concept in quant finance, and why are we reading it, right? So that objective is clear. I think I have done my job, and you also have done your job by understanding it. Okay. Now we get into your combined insight, which is your derivative integrals, how derivative integrals work together, right? We are trying to understand how both tools work together in finance. So two perspectives of the same system, basically derivatives, zoom in on your change, your risk, your sensitivity, and your motion, right? They measure your instant variation, instant reactions. Example in finance, delta, which is for sensitivity to price, your gamma, which is sensitivity to delta, your vega, sensitivity to volatility. Delta is delta V by delta S, right? And gamma is delta square V by delta S square. These measure local sensitivity, how option price react to your small price movements, small market movements. Integrals are different, right? Integrals, when you talk about integrals, zoom out over time, right? They measure your total accumulation. So whenever we are looking at, let's say, present value accumulation, right? You take 0 to t, CFT, exponential minus RT, dt, expected value, x, fx, dx, integral. We did in the previous slides, right? These measure your global outcome, meaning total value accumulated over time, right? So in quant finance, both are used very, very widely. I covered sensitivity, I covered risk, used to measure how option price react to small price movement. Integrals, I covered aggregation value, this thing and this thing. Used to compute total value, expected return, probabilities, derivative, how fast the portfolio value change. Today, integrals, total value, portfolio value computed over time, right? Key takeaway, derivative explain local behavior, integral explain global outcome, right? So keep that in mind. Derivative answers how fast portfolio value is changing right now. Total portfolio values, integral basically means total portfolio value accumulated over a year. Derivative explains your local behavior. Integral explains your global outcome. This idea drives your model like your Blackboard, your interest rate model, your risk model, right? That we need to understand. Okay. And then we go here in the practice set. Question 1, fx is equal to 3x plus 5. We need to identify your domain and range. See, when we try to understand your domain, right? Domain, what is the domain here, right? See, this is an easy question. Domain, a linear function has no restriction, right? So domain here is minus infinity to infinity, right? Linear function has no restriction, right? Okay, range. Range, interesting, right? Since your slope is not equal to 0, right? Since slope is not equal to 0, right? Output can also take any real value, right? Right? So range also is minus infinity to infinity. Again, for this one, a linear function has no restriction. Remember that. Okay. Then we go to the next question, evaluate limit x tend to 2 x square plus 3x. This is again x square function, polynomial functions are kind of continuous. You kind of substitute values. So it becomes 2 square plus 3 into 2, which is 4 plus 6, which is 10. The answer is kind of 10, very easy. Call payoff, check continuity at ST is equal to K, right? I think we have seen it multiple times, right? So if you take left side, right? If you take left side, if ST is less than K, we understand payoff is 0. If we go to right side, right? If ST greater than equal to K, right? Your payoff is ST minus K. At your ST is equal to K, right? It becomes K minus K is equal to 0, right? So both sides are equal, right? Function is continuous, right? So both sides equal. Your function is continuous. Okay. Then we go to question number 4. Given your Vt is equal to 100, exponential 0.060. If you take compute dv by dt, right? Again, you can do the derivation. If I take d by dt of your exponential, right? Let's say exponential EAT, right? It becomes AEAT, right? So if I take your dv by dt is equal to 100, right? So the A will come ahead, which is 0.06, exponential 0.06 into t. So it becomes 6 exponential 0.06, right? T, right? So that is what we have. If you have to do financial interpretation, portfolio grows proportionally to its current size. Portfolio, because growth rate is 6%, right? That is what we are getting it, right? So what we are getting it, that if I take your dv by dt is growth, na? dv by dt, right? It is 6%. The growth rate is 6%, right? 6% continuously, right? dv by dt is RBT, right? RBT we are getting. Okay. So that is what we're getting. This is the same concept which was given here also, right? If you're getting confused, you can see this. This is the same concept which was touched. dv by dt is equal to RBT, right? And dv by dt is equal to RBT, right? This part. Okay, dv by dt is your RBT. RBT, right? Another question, fx is equal to lnx, find your f dash x and state its domain, right? See, again, question number 5, if I'm doing, right? See, understand d by dx of your lnx is equal to 1 by x, right? So, again, this is how d by dx works. You have learned in your differentiation. Please understand, log is defined only for your positive number, right? So, since log is defined for only your positive numbers, right? Domain x is greater than 0, right? The positive number only, right? We go to question number 6, which is fx x square x less than 1, 2x plus 1, x greater than 1. Check continuity and x is equal to 1. Again, when we have to check continuity, right, we start with the left limit. Left limit at x is equal to 1, right? So it is 1 square, which is equal to 1. We take the right limit. Right limit, you put 1, 2 into 1, 2 plus 1, 3. Right limit, you take 3. Right? So function value f1 is 3. Left limit is not equal to right limit. Right? So function is not continuous, right? So not continuous. Okay. Then we go into next question, question number 7, right, which is here. Again, Vs is equal, if Vs and S is equal to St, you chain rule to express dv by dt, right? See, dv by dt, if I have to do, it is change in value of V for change in value of S into your ds by dt, right? When you look at your financial interpretation, portfolio change depends on your sensitivity to the asset price, which is delta, how asset price changes over time. So dv by dt, right? Delta dv by ds delta ds by dt, right? Question number 8. Now we are moving to hard question. We have given CFT is equal to 10, 0.3t, R is equal to 5. What we are trying to do, compute PV is equal to 0 to 5, CFT E minus exponential E minus RT dt, right? Not a hard question, right? Just if you substitute the value correctly, you can do it, right? So what will happen here is that PV is equal to what? 0 to 5, 10, right? 10 is a function, right? 10 exponential 0.03, right? T, right? And then you are doing what? Exponential your 0.05, right? T dt, right? So please understand this is RT, right? R is 0.05, right? So if we put it more simply now, we combine the exponents, right? So 0 to 5, 10 exponential your minus 0.02 t dt, right? And if you do integral of exponential, right? Integral of exponential, then it becomes 10, yeah, exponential 0.0 t, right? 0 minus 0.02. How do you remove this? Fine. 0 point. 0.02 and we take 50, right, which gives the numerical PV, right? So you can calculate, right? You have to just substitute the value now, guys, right? And then we are going to question number 9. Fx is equal to your given PDF. Fx is equal to 2x, 0 to x 1, right? You have to find the expected value, right? So question number 9, expected value is equal to your 0 to 1, right? X fx dx, right? That is 1, right? And in this case, what happens is that you uh, substitute the function, right? So it becomes your what? 0 to 1 x 2x dx, right? So 2 comes out, 0 to 1 x square dx, right? 2 x cubed by 3, 1 to 0, which is 2 by 3, right? So we get 2 by 3. Then we go to question number 10. Financial maths, why option payoff is continuous, right? Explain why option payoffs can be continuous but not differentiable at the strike price. Relate this to delta behavior, gamma spike at the strike. Concept is fundamental in option hedging and risk management. So basically, the idea here is that when you take the call option payoff, right? Call payoff, it is max of your S minus K comma 0. And we have seen in the graph shape, right? There was a kink, right? There was a kink at the strike price, right? K, right? And left side of strike, it was 0, right? Right of strike, again, K minus K was 0. The function is continuous, right? Now, when you look at your differentiability, right? Left side of slope is 0, right of side of slope is 1. So since slope differs, derivative does not exist at your strike, right? Slope differs, derivative does not exist at your strike, right? And if you look at relation to your delta, right? So this is what we have, right? Here, if you see, slope here is 0, slope here is 1, right? So OTM call, delta is 0, right? OTM call, your delta is 0. ITM call, delta is 1, right? And you look at gamma, right? Gamma is the derivative of delta. So because delta changes rapidly near strike in the ATM, gamma spikes in the strike price. So this is again a very, very important concept. Small kink in the option payoff explains. Small kink in the option payoff, this one explains delta hedging, your gamma risk, your option market behavior. That is why your ATM options have the highest gamma and require the most active hedging, gamma hedging, right? So that is what we need to understand, right? So this completes our this chapter, guys. Very, very important to understand. Again, little lengthy, right? But not difficult at all, right? A lot of concepts here related with financial world, but the point to understand is that this is what we need to learn and do. And we have to correlate the concepts, right? So you start with the first topic, right? So ultimately, we're covering the derivative and integral. Derivative is measuring your changes, integral is measuring your accumulation. Then we moved our derivative, Greeks, etc., delta, gamma, vega, theta, right, rho, right, and there are many more, right? Please don't think that these are only 5-1. These are the most popular 5-1. There are many more Greeks, there are 13, 14 Greeks, right? Vana, you know, speed, Zoma, Volga, right? There are many, right? So that's what we have. And then we move to integrals and we saw the use of integrals, expected value concept, very important. Questions, we did it, right? We need to understand that. Okay. All right, guys, we have completed this chapter. I'll see you in the next chapter. Till that time, go and revise this, practice it, and we'll discuss the next chapter. Okay. All right, guys. Thank you.